Good morning, Caymans. Mr. Riker here. We'll be looking at graphing rational functions today. And in this particular part of the lesson, we'll look at how to determine where vertical asymptotes are. We'll briefly mention oblique asymptotes. And we'll also talk about points of discontinuity. So in this first question, you're asked to identify the location of all asymptotes and points of discontinuity. So let's zoom in a little bit on this first one. So for the vertical asymptote, it looks like it's roughly right here at 3. So we would say x equals 3 is a vertical asymptote, VA. And it looks like we have a horizontal asymptote right about here, which looks like at -2 based on the scale. Y equals -2 is a horizontal asymptote. Now, you always have two asymptotes when you have these rational functions, or at least these basic rational functions. You can get more than two asymptotes, but we'll talk about those in tomorrow's lesson. And also, you'll notice this circle right here. This is called a point of discontinuity. So an asymptote is a very large, unfixable discontinuity in a graph. But anytime you have a point of discontinuity, we abbreviate that POD, point of discontinuity, and it looks like the point is at 2, 6. So the x-coordinate 2 and the y-coordinate 6. And we'll talk later in this lesson about how to determine where a point of discontinuity is going to occur based on the equation. But just visually on a graph, we try to make the circle pretty obvious where that point is. Now, technically that point would be really, really small, but we have to make it a big circle so you can see it. So that's it for number 1. We've identified the two asymptote locations as well as the location of the point of discontinuity. Number 2 is for you as a try this. And then number 3, we'll identify the locations. So first, the vertical asymptote looks like it's right here at x equals -1. Vertical asymptote, VA, x equals -1. And it does not have a horizontal asymptote, but it does have what's called an oblique asymptote, or we abbreviate it as OA, oblique asymptote. Now, this one might be a little bit tricky to determine where exactly it is, but I'm going to guess it's maybe like right here is the oblique asymptote. So it looks like the oblique asymptote is at the equation roughly y equals slope of 1 with a y-intercept of 2. And we'll talk about very briefly in the next part of this lesson how to determine if you're going to have an oblique asymptote based on the equation. But then the following lesson after this one, you'll learn more detail how to determine where an oblique asymptote is. So that's the first part. Let's just review how to determine where locations of vertical asymptotes are. If we were to graph 1 over x plus 2, if we were to first determine what the excluded value is, the excluded value is when the denominator equals 0. So if we take that denominator and set it equal to 0, that's going to tell us, hey, we can't have -2. And anytime that happens, that gives us a vertical asymptote. So you have a vertical asymptote at x equals -2. So we can start with that -2. And if you wanted to graph from there, you could make a table of values. Here's f of x and our x. I'd recommend put in the middle of your x's, put that vertical asymptote number of -2. Now if you plug that in, you're going to have 1 over 0, which is undefined. That's where the vertical asymptote is after all. And we'll pick a couple numbers to the left and to the right of -2. So like -1 and 0, and then -3 and -4. And then we can plug those values in and graph the points from there. Here's our table of values, and then we can graph those points, and we'll get our rational function. And there are our points, and we would get a graph that looks like this. Follow the asymptote down, pass through those 2 points. And we do have a horizontal asymptote at y equals 0. Now you might remember that's because we have a plus 0 here at the end there. So there's our graph, and that's how we can determine where a vertical asymptote is. Anytime you set the denominator equal to 0, that gives you the location. We could do the same for the next one, number 2. We can see that if we take the denominator, we set that equal to 0, we would get x equals 3 is a vertical asymptote. So x equals 3. Also, we have a plus 0 at the end here, so that would be a horizontal asymptote at y equals 0. And then lastly, we can make a table of values. We're going to put 3 kind of in the middle of the table. That's the location of our vertical asymptote. That's where the function is undefined, so we can't divide by 0. And we'll pick a couple numbers on either side of 3, like 1 and 2, 4 and 5, and plug those in and graph the points. So there's our table of values, and there are 4 points graphed. So here's our function. Notice because we had a negative for the a value up there, we're not in these 2 quadrants with the branches, but we actually flip and we're in the other 2 quadrants for the branches. And also we can include the locator point, which was 3, 0. That's from the 3 and the 0 here, 3, 0. But that's vertical asymptotes. Let's now look at a brand new idea today. Let's look at a brand new idea today about how to determine where a point of discontinuity is going to be. So first thing, with points of discontinuity occur when there's a factor in the numerator with x that will divide with the identical factor in the denominator. So this x plus 2 and x plus 2, these can divide out. That tells you anytime you have that, the location of the point of discontinuity is going to occur when you set that x plus 2 equal to 0. So you have a point of discontinuity at x equals -2. To determine where the point is, the y-coordinate of the point, we should simplify this function. If we simplify that, we get to this step, no more x plus 2's. And now if we plug in to x our -2, we would have 1 over -2 minus 2. Again, we're plugging -2 because that's our x coordinate, so plugging in x. And that would give us -1/4. So we would have a point of discontinuity at -2, -1/4. We also have, on the same graph, we also have a vertical asymptote. If we look at the simplified version here, we have a vertical asymptote at whatever can't be divided out, whatever factor in the denominator, set that equal to 0. So you have a vertical asymptote at x equals 2. So we have x equals 2 is a vertical asymptote. This equation would have a horizontal asymptote. But the new part is graphing this point of discontinuity at -2, -1/4. So somewhere right around here, -2, -1/4. Maybe I'll highlight that for a second so you can see right around there is -2, -1/4. And then we can use our usual process. So we can make a table and then graph the other points. So here's our table of values. I've graphed those points. Now when you graph, make sure you get close to the asymptote, connect it with the point of discontinuity, and then follow the other asymptote down. And then likewise on the other side. So that would be our graph. But again, the brand new thing about this graph is you have a point of discontinuity at -2, -1/4. So let's try another example of that so you can get used to the idea of of points of discontinuity. So here we should factor the denominator first. When we factor, we would get a function that equals 3 times x minus 1 on the numerator still, and we would have x times x is x squared, and then a 3 and a 1 get us to 3, and we want a plus 3 and a -1. So notice again, brand new part of this lesson is since this x minus 1 factor can divide out, that's going to be the location of the point of discontinuity. POD, point of discontinuity. So x minus 1 set equal to 0 gives you x equals 1. And then in the simplified version, so the simplified version is 3 over x plus 3. So you're going to plug 1 into that. So plugging 1 into that, we would get 3 over 1 plus 3, which is 3/4. So we have a point of discontinuity at 1, 3/4. And we can graph that. That would be 1, 3/4, right around here somewhere, is a point of discontinuity. We could also graph our asymptote, vertical asymptote at x equals -3. And it looks like we're going to have a horizontal asymptote at 0. Then we can make our table of values and graph the function. So there's our table of values and our 4 points graphed from the table of values, and I've also graphed the point of discontinuity. And again, remember the new part here is we just have a point now of discontinuity. These are actually pretty convenient. Let's say you plug in the x wrong and you get a point of discontinuity like up here. That would be a big problem. That doesn't follow the other points. It doesn't follow the function. So you know you've done something wrong if you get a point that far away. So I have a little summary spot down here. I'd encourage you to summarize, pause the video and summarize, when do vertical asymptotes occur? What does the equation look like? When do points of discontinuity occur? What does the equation look like? So here are 2 basic examples to differentiate. For vertical asymptotes, anytime you have this factor in the denominator that you can't divide it out, there's no other x plus 1 factor, that's going to give you a vertical asymptote. So they occur when you set the denominator equal to 0 and the factor cannot be divided out. Whereas with a point of discontinuity, here's an example. Notice the x plus 1s can be divided out. So these occur when you set the denominator equal to 0. That would be the x value of the point of discontinuity. And the factor can divide out with something in the numerator. So that's the basic idea of when points of discontinuity occur versus vertical asymptotes. For both of them, you're setting the denominator equal to 0 and solving, but for one of them, the factor can't be divided out, in the other, the factor can be divided out. Thanks for watching this video. I'll see you in the next video where we talk about some more details about horizontal asymptotes and oblique asymptotes.